Well, students, in the last class, we have introduced the notion of bonds and also gave some ideas about how to deal with bonds, what is the risk involved in bonds, and so on. Today, we will talk about an important concept in bond called duration. We have already motivated this idea through the price sensitivity of the bond when compared to the yields. Recall that in the last class, we have written the price as a function of yield. And then we saw that when the duration of the bond is larger, the variation in the price is more steeper with respect to the variation in the yield. So this we have seen intuitively from the expression of the price, whereas using the concept called duration, we can see the same result in a more rigorous way. That is what we are going to do in this class. As usual, let us take the period of the bond be 0 to t and let this period be partitioned into n plus 1 time, and at each time tk there is a transaction happening. The concept of duration need not be restricted only to bonds. It can be done for a general cash flow stream. So we first discuss the duration in terms of cash flow streams and then come to bonds. If you recall, once you are given the cash stream, you can talk about the present value of the cash stream. So the present value of the cash stream, if you recall, it is the sum k equal to 0 to n xk divided by 1 plus rt by n to the power of k, right? So this is what we know from our previous class, how the present value of a cash flow stream is defined. Now, given each xk, that is each entry in the cash flow, how to write the present value of that single cash flow is just a easy consequence of the general formula. It is given like this. If we take the compound interest scheme with frequency n, then it comes like this. Whereas if you take the continuous compound interest scheme, then it is given like this. So with respect to this, we can define the duration of the cash flow stream X like this. So it is nothing but the summation k equal to 0 to n, present value of each cash flow times the time at which the transaction happened divided by the present value of the entire cash flow stream. And the duration of a cash flow stream is denoted by d of x. Let us have a close look at this formula. So let me rewrite this expression as this, where I have just taken off this term separately and written like this. Now we will denote this by wk, and thereby you can write the duration d of x as the weighted sum of the times, where the weight depends on the present value of the cash flow stream. You can also see that the sum of these wk's, that is k equal to 0 to n, wk is 1. And also you can observe that the unit of duration is actually time, because this has the unit of price, and that is divided by another term which has unit price. Therefore price gets cancelled, and all these weights are basically dimensionless quantities, and therefore the duration is left out only with the unit of time. So this duration gives us a measure of the average time length that the holder of the cash flow has to wait before receiving the cash payment. This is just a rough interpretation of duration. You can see that if you take zero coupon bonds, then the cash flow is you have the initial payment P naught, and then at the end only you have the face value plus all the coupons at a time released. So you basically have So what happens is when you take this cash flow and find the duration of this, what you will get is duration as weight is everything is 0, only the previous value of the final one, that is Pn plus C will be there. All others are zeros, right? That is the zero coupon bond. You don't get payment in between. Only at the final settlement, you have the entire face value and all the coupon values added, you will get. So this, and that is also equal to the PV of X is also equal to this. So they both get cancelled and you have Tn, that is the nth year. Okay, so n. So the duration in terms of the zero coupon bond is exactly n year. So therefore it gives us a feeling that duration is going to measure the average time length that the holder has to wait before receiving the cash payment. This is a rough meaning of duration. Let's take an example. Consider the cash flow stream like this, where each transaction is made quarterly. Therefore, the partition can be taken like this. Note that quarterly means you have only 4 entries. Therefore, your interval is 0 to 1. It means T is equal to 1. And each transaction is quarterly. Therefore, the first one is happening after 25% of your entire period. Therefore, it is 0.25. In terms of month, it is 3 months. Say March, and you are paid this, and again June and you are paid this. That is the mid of your year. Therefore, we take it as half, and then you have at the end of September, you have this. This is 75% of your total period, and finally you have it in December, that is completing your 1 year. So this is the basic idea of how we can interpret this partition in terms of the time period of. So you are given the cash flow and you are given the transaction time T1, T2, T3 and T4. So we can find the duration of this cash flow provided what is the interest rate, right? Because when we are finding the present value, you need also the interest rate. Let us assume that the interest rate is given 10% per annum, and the interest is calculated compounding basis, and it is quarterly. Generally, that we always do, that the frequency of the compounding coincides with the n that comes from your cash flow stream. So you can of course see that the present value is x naught is actually 0, and the present value of x1, that is present value of 60 rupees, that is nothing but x1 divided by 1 plus 0.1 divided by 4, right? Because the interest rate is 10%, therefore R is 0.1, and you are compounding quarterly. It means in 1 year you are giving 4 times the compound interest. So therefore this is 4, and that is in my calculation approximately equal to 58.5366. And similarly, the present value of x2, that is approximately equal to 57.1089, and similarly PV of x3, which will have 60 divided by 1. Sorry, this is here. Okay, so 60 divided by 1 plus 0.1 divided by 4, the whole cube, that is approximately equal to 55.7160. And finally, present value of x4 is approximately equal to 54.3566. 70. And if you recall, I think this example we have already calculated and found the present value of the entire cash flow stream is 225.7185. So once you have this, what is the duration of the entire cash flow? The weighted sum of the time where the weights are calculated from the PVs. So with all these numbers, the weight W0 is 0, W1 is 58.5366 divided by 225.7185, and similarly the other weights you can find. The other weights are given like this, and therefore the duration of X can be calculated, and it is given by approximately 0.6173. So roughly what happens is the duration, that is the person in an average has to wait for this much percentage of the total period. Suppose if it is 366 days is the total number of period of the cash flow stream, then this will amount to around 225.9318. This is just a rough estimate of the duration that the holder has to wait in order to get the payments. So this is just a rough estimate. You can see that the cash payment is distributed equally. That is why the average is coming very close to 0.5. Okay, if the cash flow is say 5, 5, 5, and then everything else is given like this, say for instance 225 here, okay, then the duration will go very near to 1. Okay, that's the average time that you have to. So it depends on how your cash payment is distributed in your cash flow stream. Okay, accordingly the average time that one has to wait will come. So this is just like a rough estimate, something like, if you want to know what is the average performance of a class, we take the average marks scored by the students, like, so it's like that. From the way we define the duration, we can clearly see that it can be applied to any cash flow stream. In particular, it can be applied to bond, and in this case the duration is called the Macaulay duration. We will now discuss how we can measure the sensitivity in terms of duration. Again, whatever we are going to discuss can be carried over for any cash flow stream, but mainly it is used in the context of bonds. Therefore, we will restrict ourselves to bonds. If you recall, we had the yield price curve for maturity being 30 years. So here, if you take a small variation in yield, let us call this as delta R. Correspondingly, we will have a small variation in the price, which will be roughly given like this, delta P. Okay. Now, our interest is to relate these two. How to relate these two? That is, delta P is what we want, given delta Y, or delta Y we want to measure in for a given delta P. So this is equal to, what is this factor that relates these two quantities? That is the question that we would like to pose now. So what we will do is take any yield R and a small variation in yield, say delta R. Then you can apply the mean value theorem to get delta P. Say this is R and this is R plus delta R, and that corresponds to, this is P and this is P plus delta P, right? So delta P is nothing but P of R plus delta P. So delta P will define as P of R plus delta R minus P of R. By mean value theorem, if P is continuously differentiable, just assume this for the sake of theoretical derivation, then we get this expression directly from the mean value theorem. So as he said, delta P can be related to delta R through this. Okay. Now we have to get a precise idea about how it looks like. How are we going to go about with this? Well, we already know what is P in terms of R, right? Let us recall that. P in terms of R is given like this. In the last class we have seen. In fact, we have also seen what is P dash of R, right? P dash of R is given like this. You directly differentiate this expression with respect to R. Okay, so you have so 1 plus R by M, this, and then you have this, and then R by M, when you differentiate, this M will come and sit here. And similarly, here you have 1 plus R by M J, therefore J into this to the power of minus J minus 1, and then differentiating R by M will give 1 M here. So what I'm doing is the same expression I'm rewriting like this. Let us try to understand this. What I did is this J, I simply carried over here. And this 1M I have carried over here. And this part I just kept as it is. And remaining the C by M, I have written as XJ. Okay, I hope you can see this without any problem. So once you understand this, these xj's are precisely C by M when up to n minus k minus 1. The last term, you have to combine these also, right? Therefore, the last term x n minus k will be, well, C by M is coming from here, from the last term, and Pn is precisely coming from here. So this is how I have written P dash. So let's see further how we can go about. I want to put this expression into what we have. Delta P is equal to this. So here, if you recall, we had actually mean value theorem gives us delta P is equal to P dash of some rho times delta R. What is rho? Rho is some number which lies between R and R plus delta R, right? But this number, as per mean value theorem, is an unknown number, because mean value theorem says there exists a rho such that you can write this. But we somehow want a precise formula. Therefore, what we will do is assume that this delta R is very small, and you just take approximately rho equal to R. This is just an approximation because we don't want to hang around with an unknown quantity. Okay. So once you put this approximation, you have P dash of R instead of rho. Now we have this P dash given like this from our previous derivation. Now observe that this is nothing but Tj, right? J by M. So in the last class, we have used this many times. And what is this part? And what is this part? You can see that PV of Xj is nothing but Xj divided by 1 plus R by M to the power of J. We precisely have this here, Xj divided by 1 plus R by M. J alone is there. Okay, so this part is not there. Therefore, that alone I can replace by PV of Xj. So that's what I am doing here. P dash of R equal to this minus sign, sigma 1 to n minus 1. This part leaving minus 1, I put Pj, and this entire thing minus 1, I retain as it is, and j by m, I put Tj. So therefore, now you see, this resembles something, okay? What? If you recall, what is D? D is nothing but sigma j equal to 0 to n minus k PV of xj by PV of x, right, into Tj. In bonds, generally we take Tj, T0 to be 0, right? So therefore, we can put this part, that is, we can put this part as Tj into PV of x. So that's what I'm doing. P dash is equal to this part multiplied with PV of x, because D is nothing but this divided by PVJ. Therefore, you get this. And what is this M? I will just merge it with the D and call that as M. Okay. So dm is d of b, which is the duration, divided by this term I carried over. Generally in literature, it is called modified duration. What is this b? B is the bond cash flow. Okay. Of course, there is a P naught here, which we will take as 0, but you have to start with 1 and then going. So this is x1, therefore x2 up to xn. Okay. Ideally, I should have put a 0 here, and that I should have taken as x0. Okay. So that you can add in your notes. Okay. So this is what is obtained finally. So we obtained P dash of R equal to minus dm, that is the modified duration, times the price. Okay. Recall, we had PV of B. PV of B is nothing but the price only. Okay. The price is defined as the present value of the cash flow. Okay. That is why I have replaced PV of B as price itself by definition. Okay. This ordinary differential equation is what is called the price sensitivity model. Okay. You just substitute this in this place, you get the relation between the change in price versus change in the yield. Okay. So I have just brought this P, so that what this represents, this is nothing but the relative change, that is the percentage change in the bond price. Note that delta R being the yield, it is already a percentage. Okay, therefore this also represents the percentage change in the yield. Okay, so the percentage change in the price is related to the percentage change in yield by a factor minus dm. So that is why this duration is very important concept. This measures the impact of yield variation in bond price. The price sensitivity model, that is this equation, is derived on the basis of the discrete compound interest. You can also do it for continuous compound interest. I will leave it as an exercise to you. Let's have an example. Consider a 2-year bond with face value being 100 rupees and the coupon rate is 10%, with a coupon payment being semi-annual. Okay, so these are the key inputs that one has to collect. So with this much, we can actually write the cash flow stream of the bond. Now to get the issue price, we need the yield rate, that is R, right? So at the issue, the yield rate on the bond is set to 12%. That is, R is given to be 12% per annum with compounding semi-annual. Okay, so these are the keywords for setting up the present value of the cash flow stream. So with the first part of the input, you can write the cash flow stream. Generally take X naught to be 0 because we need to write the present value only for the coupons and the face value, right? So we take X naught to be 0 in obtaining the price sensitive model. So the coupon rate is 10% and it is given semi-annual. So 10% means 10 rupees per annum you are getting because the face value is 100 rupees. So coupon is always paid on face value. Therefore, it is 10 rupees per annum and the payment is given semi-annual. Therefore, after 6 months, you get 5 rupees and then after another 6 months, that is after 1 year, you will get another 5 rupees and so on. So this is T equal to 0.5, T equal to 1, 1.5, and then it's a 2-year bond. Therefore, after 2 years, the bond closes. Therefore, the face value 100 plus the last installment of the coupon also comes. So you have this. So you first have to carefully write the cash flow stream. That is the main part of this problem. Once you have the cash flow stream, remember we have to make PV of XJs and PV of your cash flow stream B. So these two things we have to obtain in order to build the price sensitive model. Remember, to build price sensitive model, we need the duration, that is modified duration you need. So let us compute the present value of each of these coupons. So PV of X1 is 5 divided by this one, the first one. Therefore, the discount factor is just this. Why you have 0.12? Because the yield rate is 12. Don't confuse it with the coupon rate. Okay, yield rate is R, which is sitting in the definition of your price, whereas coupon rate gives you what is the value of C. Remember, C is 10 and M is 2 because it is semi-annual. And what is N? N is the number of years, that is the maturity, that is 2. Therefore, capital N, that is the number of payments, total payments is 4. That is M into N. That is why we have 4 terms here. So PV of Xn is C by M, right? That is 5 divided by 1 plus R. What is R? R is the yield, that is 12%, 0.12. Don't confuse it with the coupon. Coupon is C, whereas yield is the one which is sitting in the denominator, that is the discount factor in the price. Okay, therefore that has to come. Don't put 0.1 here. So the 0.12, that is the yield we have to put, divided by the compounding is semi-annual. If this is different, then it will be different here. Okay, generally we take the compounding same as the M. Okay, that generally we will do, but need not be the same. So this 2 is actually because the compounding is semi-annual, and that in my calculation comes to be like this. And then PV of X2 is again C by M or by this compounding, which is equal to M. Therefore, I will put M here. Okay, generally we take that, but one has to be careful. And then this is the second term. Therefore, 2 discounts are happening. So this is the first one. X1 is discounted only once, whereas this is discounted twice. Okay, and that comes to be this. Similarly, PV of X3, the same formula, but 3 here. Okay, that gives me PV of X3. And PV of X4 is, what is this one? This is 105. Remember, don't put 5 because here it is coupon, that is C by M plus PN. PN is the face value, that is 100 divided by 1 plus 0.12 divided by 2 to the power of, now this is 4 times you are discounting, therefore it is 4. And that gives you this time. So now we got all the PVs of single cash flows. Now the present value of the entire cash flow stream B is nothing but the sum of all these things. Okay, this is 2 here. Sum of all these terms, that happens to be this, which is also, if you recall the theory of bond, this will be the issue price if the issuer fixes 12% as annual yield. Now we will go to calculate the weights. How weights are given? Recall, weights are nothing but PV of XK divided by PV of the entire cash flow. That is the weights. So W1 is this divided by this. W2 is this divided by this, and so on. W3 is this to this. W4 is PV of X4 divided by PV of B. So that gives, you can add them up. Obviously, they will then add everybody to 1. Okay, so we got all the basic parameters. Now we can go to compute the duration. So all the basic parameters are computed and kept. Now we will go to find the duration. Since it is a bond, I will call the duration as Macaulay duration. It is given by W1 T1. Remember, it is semi-annual, therefore T1 is half, W2 T2, W3 T3, and W4 T4, maturity. And that happens to be this. So this is the duration, but in price sensitivity, we want modified duration, right? So the modified duration is nothing but duration divided by 1 plus 0.12 divided by 2. In this particular example, it is this, and that gives me this value. Now we are ready to write the price sensitivity model. We collected all the parameters. The price sensitivity model is nothing but P dash is equal to minus dm times P. Okay. So once you have, you can also write delta P by P is also minus 1.7536 times delta R. Okay, so that is the relation between the percentage change in the price versus the change in yield.